Welcome to PyTorch, Techniques and Ecosystem Tools. It's the second course in the PyTorch Professional Certificate. I'm joined once again by Lawrence Moreau. In this course, you focus on optimizing model performance and building more advanced architectures. So you see how to take basic building blocks and quickly combine them into much more complex, much more advanced neural network architectures.
In the first part of the course, we're actually going to tackle one of the biggest challenges in model optimization with hyperparameter tuning. There's so many ways that you can do it, including writing your own code for rough searches or using tools like Optuna from the Python ecosystem. Once I've designed an architecture that works, it's rarely optimal. There's all these choices that I have to make. Do I build deeper? Do I build wider? What kind of optimizer will I use? We'll actually start with giving you the tools for hyperparameter searching and neural architecture search. And then we'll teach you how to build these models from scratch, computer vision models and natural language models, before overlaying these with like transfer learning from existing models and then doing fine tuning on them.
You will learn a lot of those key building blocks, things like tokenization, pre-training, fine-tuning, that have been key to really everything happening in AI around us. And that maybe even more importantly, will give you key skills able to navigate all of these very large and important portfolios of technologies.
And then to bring it full circle, we'll go back to optimization to take a look at, are we efficiently loading data from the drive to the CPU, to the GPU? Are we having things hanging around waiting when they could be working? And like to just look at the various tools and techniques that we have to be able to squeeze the most optimization that we have out of that, because the faster we can train accurately, the quicker we can actually iterate on this.
I think you enjoy this course where you go from the basics to understanding a lot more sophisticated concepts in how to build deep learning models. Let's go on to the next video where we'll start with hyperparameter search.
I'm excited to welcome you to the second course in this professional certificate. I'm Lawrence and I'm going to be your instructor. In the first course, you were introduced to the fundamental components of PyTorch, enabling you to build and train simple neural networks. In that initial course, you built a robust foundation in PyTorch, including creating data pipelines, building and training models, evaluating performance, and inspecting what's happening under the hood. And you applied all of those skills into a project where you created an image classifier for a botanical garden. This second course goes deeper into building more powerful and efficient PyTorch models. And we're going to do that across 4 modules. In Module 1, you'll learn to optimize your models by testing and tuning various hyperparameters, such as the learning rate, the number of layers, and the batch size. You'll see how subtle changes can have a big impact on key metrics like accuracy. In Module 2, you'll explore image data using torch vision. You'll see how to apply transformations for image preprocessing, use built-in models and datasets, perform data augmentation, and work on challenging problems like image segmentation. In Module 3, you'll then turn to text data. You'll apply text embeddings, use transfer learning, and tackle advanced challenges like text classification. You're also going to be using some models from Hugging Face. And then in Module 4, you'll focus on making your training pipelines more efficient. You'll use profiling tools to identify and resolve bottlenecks so your model can train faster and scale better. Please be aware that certain concepts from our previous course will be revisited and explored in greater depth in this course to ensure that if you're coming straight from course 1, or even if it's been a while since then, you will still encounter familiar concepts introduced again here so that you get the full story. For this first module, we'll begin by discussing model optimization. At its core, optimization is about finding the best possible value of a function, like a maximum or a minimum. In machine learning, this often means adjusting parameters or architecture to improve some objective metric, such as accuracy, speed, or memory efficiency. Imagine you wanted to sell that plant identification app you created in course 1 through an app store. You'd try different subscription prices, and then you'd track how much revenue you earn. If the price is too low, you'll get lots of downloads, but you won't make much money per download. If the price was too high, well, only a few people would download it, even though each download brings in more revenue. So what's the best price to choose? You can think of price as a hyperparameter. And just like in a machine learning model, there's an optimal value that gives you the best result. In this case, a moderate price point maximizes your total revenue. Throughout this module, you'll apply that same mindset, tuning and improving your models by finding what works best for your goals. So let's get started with Module 1. Welcome back! In this video, you'll dig deeper into the concept of optimization. At its core, optimization involves finding the best possible value for a function, and that's usually a maximum or a minimum. In machine learning, this often means tuning your model to achieve the best possible performance according to a metric like accuracy, precision, or recall. Let's revisit the app that you developed for the botanical garden in Course 1. The goal there was to identify flower types from images, and you aimed for high accuracy. Suppose that after building and training your model, you achieve an accuracy of 48%, meaning that the model correctly predicts the flower type in 48% of cases. Well, how can you improve on those results? One way is to adjust hyperparameters, which are settings that control how your model trains. One such setting is the learning rate, which determines the step size used by the optimizer during training. To understand how the learning rate affects accuracy, you can create a graph with the learning rate values on the x-axis and the corresponding accuracy on the y-axis. Accuracy may be 48% at the current learning rate. If you were to test various learning rate values and determine the accuracy for each one, the chart might typically look like this. If the learning rate is too small, training can be slow, and the results may stagnate at suboptimal positions, resulting in low accuracy. If it's too large, the model might bounce around and never converge, also resulting in low accuracy. But somewhere in between is an optimal learning rate that maximizes accuracy, and this is the value that you should aim to find. Here's a chart that shows this exact pattern taken from the lab that you'll complete right after this video. You can see that performance is low at both ends of the log scale, while it peaks in the middle, forming an inverted U-shaped curve. This illustrates that there's an optimal learning rate that gives the best performance. In short, the aim of optimization is to fine-tune hyperparameters, like the learning rate, to maximize outcomes such as accuracy, precision, recall, or F1 score, or to minimize metrics like training and inference time, mean squared error, or log loss. The learning rate is just one of many hyperparameters that we can tweak, and throughout this module, we'll explore several others. But before diving into model-specific enhancements, it's important to consider external factors that could be limiting performance. For example, do you have enough data? If your flower dataset lacks enough examples of a particular species, your model won't learn to recognize it well. By gathering more images, perhaps from open datasets, you can improve the model's performance. Also think about data quality. If labels are noisy, like a daffodil mislabeled as a sunflower, the model's learning will be compromised. Even the best model will be limited by the quality of its data. And as the saying goes, garbage in, garbage out. You should also evaluate feature representation. If your training images are noisy, blurry, or low resolution, the model may struggle to find useful patterns. Getting higher quality images or applying pre-processing techniques, such as resizing or cropping, can enhance visual feature distinction. Once your data is in good shape, you should focus on internal model improvements, which is the main goal of this module. This involves adjusting hyperparameters, including the model architecture design. Some examples include experimenting with different numbers of layers in your neural network, addressing overfitting by testing various dropout layers, experimenting with different batch sizes when training, and of course, adjusting the learning rate. All of these adjustments, whether changing layer sizes, dropout rates, or optimizer settings, are central to model improvement. Throughout this module, you'll explore techniques to automate this process, making your optimization efforts even more efficient. Welcome back! In the previous video, you explored a variety of hyperparameters that can be adjusted to enhance your models. You saw how selecting the appropriate values for parameters like the learning rate and the type of scheduler can significantly influence performance. Now, I'd like to show you how to design a flexible architecture that lets you easily test different configurations. In this video, you'll see one example, but you can expand on it and adapt it based on your own needs. I'll begin by designing a flexible architecture that works with the CFAR10 dataset, which, as you may recall, is an image dataset consisting of 10 classes of various objects and animals. The first part of the architecture is the input block, where batches of images are processed. Next comes a series of convolutional blocks. Each block is composed of a convolutional layer with a ReLU activation function and a max pooling layer. You can control the number of blocks with the n layers parameter, and you'll also define two lists: n filters, which indicates the number of filters per block, and kernel sizes to specify the kernel size for each block. Then the output is flattened to prepare it for the next stage. The next section contains two fully connected linear layers. The first hidden layer will have a parameter called FC size to determine the number of neurons, while the last layer is fixed at 10 neurons because the dataset contains 10 classes. You'll also incorporate a dropout layer before each linear layer, with the dropout percentage defined by the dropout rate parameter. At the end, you'll have a complete, flexible architecture with 5 tunable hyperparameters. Let's look at how this works in code, starting with the convolutional blocks. You can define a class called FlexibleCNN, inside of which you create an empty list called blocks, where you'll store each convolutional block. Then you'll loop through n layers, which you'll pass in when you're initializing the model. Each iteration of the loop will build one block. Each block is composed of 3 parts: a convolutional layer, a ReLU activation, and a max pool layer. You wrap these in a sequential method, which lets you treat the 3 layers as a single unit. Notice that in channels starts at 3, since CFAR images are RGB. After each block, you'll update in channels of the next block to the out channels of the current block. This ensures that the output of one layer correctly becomes the input to the next. By building the code this way, you can build as many convolutional layers as you need by just changing the n layers parameter. This also ensures that each block is connected properly to the next, regardless of how many blocks you decide to use. You can also vary the number of filters and the kernel size for each layer. These are critical architectural hyperparameters that will affect how the model learns to detect patterns. Instead of using fixed values, you define 2 parameters: n filters and kernel sizes. Each of these is a list, where the ith element gives you the configuration for the ith layer. So, if you want the first block to use 64 filters with a 3x3 kernel, and the second to use 32 filters with a 5x5 kernel, you define n filters and kernel sizes as shown here. In the loop, you retrieve the values for each layer from these lists. Padding is calculated as kernel size minus 1 floor divided by 2 to keep the input and output dimensions the same. This technique is called same padding, and it helps you keep track of the feature map size across different layers, which is especially useful when your input dimensions are small, like in CFAR 10. When building flexible architectures, one important practical challenge is tracking the size of the data as it flows through the layers. And this is especially true in CNNs, where the spatial dimensions of the feature maps will change after each convolution and pooling operation. Recall that each image in CFAR 10 is 32 by 32 pixels with 3 color channels. In your flexible architecture, each convolutional block ends with a max pooling operation that reduces that spatial size by half. So as you add layers, the feature map will become smaller. In this example, you go from a 32 by 32 all the way down to a 4 by 4 after just 3 blocks. Once the feature extraction stage is done, you flatten the output before feeding it into the fully connected layers. But there's an issue. You can't compute the exact flattened size ahead of time because it depends on the size of the input images, the number of blocks, the kernel size, and the number of filters in the convolutional layers, which you may not know a priori. So you wait until the first forward pass to know the exact size of the flattened feature vector. This ensures that you always allocate the correct number of input units for the first fully connected layer, regardless of how many convolutional layers you choose or what their configurations are. In your flexible CNN, you can also treat the dropout rate as a tunable hyperparameter, and this allows you to control overfitting during optimization. Here's how it looks inside the create classifier method. In this case, dropout is applied before each linear transformation to help regularize the decision-making layers of the model. Another key hyperparameter is FC size, and this controls the number of neurons in the fully connected layer. A larger FC size can give the model more capacity to represent complex decision boundaries, but it also increases the risk of overfitting, and it requires more data to train effectively. Parameterizing it will help you explore that trade-off between model capacity and generalization. In your flexible CNN, you pass FC size as a parameter when initializing the model, which is then used directly in the classifier definition. Here, you can observe the linear layer whose input dimension is the flattened size that's coming out of the convolutional layers, and its output dimension is our parameterized FC size. Finally, the classification head takes that fully connected size as input and has an output of 10, matching the number of classes in CFAR 10. This flexible design has huge benefits. It means you can pass in different values for key hyperparameters, and the model will adapt automatically. Even if you're doing manual tuning, a flexible model like this one saves time and helps you test ideas faster. In the next video, I'll show you a tool that pairs with this flexible CNN design to test different hyperparameter configurations automatically, and it will allow you to optimize your model quickly. In the previous video, you built a flexible CNN architecture capable of adapting to different hyperparameter values, such as the number of convolutional blocks, filters, kernel sizes, dropout rates, and the size of the fully connected layer. This adaptable design is essential for effective hyperparameter tuning to optimize outcomes. The next step is to identify which combinations of those parameters will deliver the best performance. In this video, you'll learn how to efficiently search that space using Optuna, an advanced hyperparameter optimization framework that integrates with pytorch and other machine learning libraries. Imagine you want to tune two hyperparameters, each with 5 possible values. This will result in 25 possible combinations that you have to evaluate. On the left, you'll see a representation of this process, with each black dot symbolizing one of the 25 possible hyperparameter trials. A grid search involves exhaustively testing each combination of hyperparameter individually until the entire space is covered. At the end, you select the hyperparameter values that produce the best results. This method is really time-consuming since it tests all possible combinations. Alternatively, you can use random search, where only a random sample of hyperparameter combinations is tested. If lucky, this approach may stumble upon optimal values, but this is not guaranteed. Although it's usually faster than grid search, it doesn't learn from previous results, and it's likely to waste time exploring unpromising regions of the space. A third method involves using Bayesian optimization algorithms, especially the tree-structured Parson estimator, TPE, used by Optuna. This algorithm begins by randomly selecting a hyperparameter combination and refines its guesses by focusing on regions that are likely to yield better results as more data is collected. TPE is faster and less computationally intensive, as well as more likely to find optimal hyperparameters, compared to things like the random search or the grid search. In this video, you'll explore using Optuna to optimize the results from the flexible architecture model that you previously built by fine-tuning hyperparameter selections using the CFAR 10 dataset. You'll define the search space, run an optimization study, visualize results, and then identify the best performing configuration. Your search space will comprise 5 hyperparameters: the number of convolutional blocks, n layers, how many filters to use in each convolutional layer, n filters, the size of the convolution kernels, kernel sizes, the dropout rate, and the number of neurons in the fully connected layer, FC size. To begin, you'll specify these hyperparameters within the objective function, which encapsulates the entire model training and evaluation process. First, you define the number of convolutional blocks. Using the trial object in the objective function, you can specify an integer range from 1 to 3. Each time the objective function runs, a new value within this range will be selected. Next, for each layer, set the number of filters. Since n layers is variable, you can define a list where each value represents a total number of filters per layer, ranging from 16 all the way up to 128. You'll then specify the kernel size for each convolutional layer. This also depends on the number of layers, therefore we use a list to indicate a kernel size of either 3 or 5 for each layer. These odd-numbered kernel sizes are common in CNNs for their spatial symmetry in feature extraction. You'll also define the dropout rate to prevent overfitting during training, allowing any floating point value between 0.1 and 0.5 and applying the same value to both dropout layers. Finally, you'll specify the number of neurons in the fully connected layer before the classification head, which controls the capacity for complex decisions. This value will range from 64 to 256. By defining these parameters using trial.suggest methods, you create a dynamic search space. Each time Optuna calls the objective function, it will make smarter selections based on prior results. Although there are other tunable hyperparameters like the learning rate, batch size, and the number of epochs, for this demonstration, you'll keep them fixed. That said, if you're optimizing the learning rate with Optuna, you'd use a float-valued suggestion, specifying a range, and searching in a logarithmic scale. Optuna requires a single metric to optimize, which in this case is validation accuracy. With your objective function ready, the next step is to create an Optuna study and initiate the optimization process. An Optuna study records all tried hyperparameter combinations and the outcomes of each trial and identifies the best configuration. In this example, the goal is to maximize accuracy as returned by the objective function. When you initialize the study, you specify the number of trials to run. The study.optimize function executes the objective function 20 times, each with different sets of hyperparameters proposed by Optuna. A lambda function wraps the objective function call, accounting for the trial argument and device setting, whether you're using CPU or CUDA. Let's analyze the study results. One of the most informative visualizations is the optimization history plot, which shows the accuracy obtained in each trial and its progression across trials. The x-axis represents trial numbers, and the y-axis reflects the objective value, validation accuracy. Blue dots show each trial, and the red line tracks the best accuracy across trials. Note how accuracy increases in the first few trials. But in some trials, accuracy decreases, and the red line is maintained at the value of the best accuracy up to that point. You continue for the remaining trials until you find the trial that produces the maximum objective value. Another powerful Optuna feature is its ability to determine and visualize each hyperparameter's relative importance. The plot shows the relative significance of each hyperparameter's impact on model performance. Optuna calculates importance by evaluating how parameter changes across trials correspond with objective value variations. The percentages represent their relative contribution to maximizing accuracy, and their sum adds up to 1. In this image, the number of convolutional blocks, n layers, shows the highest importance, signaling it as a crucial parameter. And you should focus on the top influential hyperparameters when resources are limited. A practical hyperparameter optimization strategy involves locking parameters one by one. By pinpointing the most impactful hyperparameter, you can fix it at their best value. This reduces the search space for future studies, allowing you to concentrate on the remaining parameters. The process then repeats as we iteratively lock additional important hyperparameters one at a time. Optuna also offers a parallel coordinate plot, which helps visualize the combinations of hyperparameter relationships to the objective value. On the x-axis, you have the names of all the hyperparameters, including the objective function in the first spot on the left. You also have a color bar that represents accuracy, where darker blue represents higher accuracy. Each line corresponds to a trial. The simplest way to read this chart is to look for clusters of dark lines converging at specific values on each vertical axis. Those clusters will point to hyperparameter settings that will tend to produce the best accuracy. For n layers, you can see that the darker lines cluster heavily at 3. And that means trials using 3 convolutional layers tend to achieve higher accuracy. For n filter 0, which controls the number of filters in the first convolutional layer, the best performing models cluster towards higher values. You can apply this same analysis on each of the hyperparameters. This plot can give you important insights into the effects of interactions between hyperparameters. When your Optuna study concludes, you can extract the optimal hyperparameter values that maximize the objective value using the best trial method. Here, we highlight the top validation accuracy with this combination of hyperparameter values as shown in the study output. Variations from these results are expected when running studies for yourself, since some level of randomness is inherent in deep learning models. You can then use these refined parameters to instantiate and retrain your flexible CNN model with a complete training and validation set. In this video, you explored the full process of hyperparameter and architecture optimization with Optuna. You constructed a flexible CNN, defined a search space with trial suggest calls, and created an objective function. You then executed an Optuna study to extract optimal parameters. Remember, hyperparameter optimization is both a science and an art. It requires strategic iteration, solid baselines, and cultivated intuition. The more you practice, the more you'll sharpen your instincts. Welcome back. In Module 1, you became proficient in optimization. From tuning hyperparameters and designing a flexible architecture to using libraries like Optuna for hyperparameter searches and balancing model efficiency. Now in Module 2, we're going to switch our focus to computer vision, specifically exploring the Torch Vision library. Deep learning for computer vision offers great potential, but it also comes with complexity. You need to manage tasks like image loading, data augmentation, normalization, batching, model definitions, visual debugging, and a whole lot more. Writing all this code from scratch can be time-consuming, prone to errors, and challenging to maintain. Thankfully, Torch Vision simplifies this process by packaging common functionalities into a cohesive library. By using it, you gain consistency as it integrates seamlessly with PyTorch's dataset and data loader modules, efficiency, given that many transforms are optimized in C or Torch script, and reliability. Standardized code reduces bugs and enhances reproducibility. In essence, Torch Vision allows you to focus on solving your unique computer vision challenges without needing to reinvent fundamental tools. Torch Vision provides tools in 4 key areas: transforms, utility functions, datasets, and models. In the upcoming videos, you'll explore each of these in detail, but for now, let's take a high-level overview of each of them and their importance. Let's start with transforms. Transforms are image preprocessing and augmentation operations applied before feeding images into a model. These include resizing, cropping, rotating, and a whole lot more. Torch Vision provides functions for all of these and allows you to create custom transformations. You also have utility functions. These functions simplify image management. Here are a few that you'll use at the start of this module, with a lot more to follow in a later video. Decode image. This loads images such as JPEGs or PNGs and converts them into tensors, which is the required format for deep learning models. After loading and converting, you can explore the tensor's dimensions and data type. Note that Torch Vision orders dimensions as channels first, and then height, and then finally width. This is different from other Python libraries like Pillow or OpenCV. The data type is uint8, given that pixel values range from 0 to 255. MakeGrid arranges a batch of image tensors into a single grid, and it's really useful for quickly visualizing batch contents. First, import TorchVision's utils module containing MakeGrid. Then use a helper function to load 6 images, and then call MakeGrid with nrow equals 3 to arrange them into a grid with 3 images per row. Padding parameter adds spaces between these images, and normalize equals true scales pixel values to a 0 to 1 range, which is essential when you're visualizing raw tensors. Save image allows you to export the tensors back into image file formats like JPEG or PNG. Now let's take a quick look at datasets. TorchVision includes ready-to-use datasets for various computer vision tasks, including classification, detection, segmentation, and video analysis. These datasets have standardized formats and are compatible with PyTorch's data loader, which eliminates the need for manual file downloads, extraction, or even custom parser writing. You'll use some of those datasets throughout this module. And finally, TorchVision even includes built-in models. Now, these are pre-configured architectures that can either be trained with your custom data or loaded with pre-trained weights for things like transfer learning or fine-tuning. Some well-known examples include VGG16, which is a deep CNN architecture that's known for its simplicity and uniform layer design. Or there's ResNet50, which introduces deep residual connections to enable very deep networks. And there's GoogleNet, which uses inception modules to process multiple filter sizes in parallel. Here's a code snippet for loading the ResNet50 model with pre-trained weights, and TorchVision lets you do this with just one line. As you can see, TorchVision is a vital part of the PyTorch ecosystem when working with images. It provides powerful production-grade tools for loading and transforming data, visualizing image batches, accessing standard datasets, and using pre-trained models. TorchVision takes care of the repetitive aspects of computer vision, allowing you to focus on developing innovative solutions. In the next video, you're going to dive into transforms, creating transformation pipelines, including different augmentations, and using TorchVision's tools to prepare your data for modeling. In the last video, you explored some common image transforms such as resizing, cropping, and normalizing. Now I'm going to demonstrate how to combine these multiple transforms into a single pre-processing pipeline using Compose. You'll also discover data augmentation transforms and how to create your own ones to improve model generalization for tasks that are specific to your dataset. Suppose you want your images to follow a specific sequence of pre-processing steps, such as first resizing them and then applying a center crop before converting them to a tensor and finally normalizing them. TorchVision allows you to create such a pipeline within a Compose function. In code, it would look like a list of operations to be applied in sequence. First, you resize the image. Then, you apply a center crop. You'll convert it to a tensor. And finally, normalize pixel values using the mean and standard deviations from ImageNet. With this setup, any image passed through the pipeline will be the correct size, format, and scale for deep learning models like ResNet. And since everything is defined in one place, it's easy to reuse and maintain consistency across datasets. These pipelines become particularly useful when integrated with data loaders. When you define a transformation pipeline and pass it to a TorchVision dataset, the transformation is automatically applied to every image entering a batch. Every time a data loader receives a sample, the pipeline will transform that original image. Transformation pipelines built with Compose help you solve a common challenge in computer vision, and that is having a small dataset. Even if you have a good architecture, your data might be too limited to train it effectively. One solution is to create variations of each image by adding things like color jitter, rotation, noise, random crops, and random resizing. And this is known as image augmentation. Each new version of the image effectively becomes a new sample added to your dataset, increasing your data size and variety without requiring you to collect new data. TorchVision offers a range of random transformations that introduce these types of variations to your training images. Here's an example of a data augmentation pipeline that performs several randomized operations. It resizes and crops the image at random, and randomly flips the image horizontally, and also adds random color jitter, and it also finally converts it into a tensor and normalizes it. In this video, you'll look at a few of these random transformations. However, the list is extensive, and I encourage you to review them in the Torch Vision documentation. The code for the composed transform pipeline is presented here. Random resized crop randomly crops and resizes different parts of the image, encouraging the model to focus on all object areas, not just the center. In this example, Torch Vision randomly cropped the original image and resized it to individual 224 by 224 images. Random horizontal flip randomly flips images horizontally with a default probability of 0.5, and this can help the model learn objects can appear in either direction. And here's an example where the flip was applied. Finally, color jitter adjusts brightness, contrast, and saturation randomly to make the model more resilient to lighting variations. In this case, these parameters were altered by a factor that's randomly selected between 0 and 0.5. And here, the output image is much brighter than the original, showing the effect of a random color jitter. These augmentations are powerful because they're effectively generating new training samples, saving you the trouble of collecting additional images. After applying random transformations, you can convert your images to tensors and then apply normalization. Torch Vision also supports custom transforms, which is helpful when you need a transformation that's not built in. For example, you could add salt and pepper noise, which randomly places white and black pixels in an image, and this simulates a grainy photo, helping the model adapt to imperfect real-life images. To create a custom transform in Torch Vision, you'll define a new custom class, and I'm going to call it salt and pepper noise. In the initialization method, define two float parameters, one for the salt to pepper ratio, indicating the proportion of white versus black pixels, a 0.5 ratio would result in equal amounts, and the other for the total noise amount, which controls how much of the image is affected. In the call method, copy the original image to which you would want to apply noise. Then add salt by selecting a number of random coordinates based on the amount parameter and setting those pixels to white with a value of 255. Then add pepper, selecting random coordinates and setting those pixels to black with a value of 0. Finally, return the modified image. Once the class is defined, you can apply the custom transform to your entire dataset by adding it to your augmentation pipeline with a single line of code within the compose sequence. And salt and pepper is just one noise type that you can add. You can explore many others like Gaussian noise, which applies random variations to some pixels, commonly simulating degradation found in some datasets. Or Poisson noise, which simulates image degradation under low light or low signal conditions. The noise type you choose should align with the conditions that you're training for your model. By all means, go take a look at other noise types that you might find useful. And as you've seen, Torch Vision's transformation system is versatile and flexible, handling basic image conversions, standard pre-processing steps, powerful augmentation strategies, and even custom user-defined operations. All of these functionalities integrate directly into PyTorch data loaders, and that seamlessly fits into your training pipeline. In the upcoming lab, you're going to get hands-on practice with these transformations. So I'll see you soon. An important aspect of solving machine learning problems is selecting appropriate data. Having enough of the right type of data is crucial to train machine learning models. Thankfully, Torch Vision makes it easier by providing the tools to work with various types of data. First, Torch Vision gives you access to pre-built datasets. These datasets usually come with labels and are formatted in a way that you can integrate them into PyTorch's training pipeline directly. That means you can train models and compare them with established benchmarks like MNIST and ImageNet. This facilitates evaluation, progress tracking, and faster deployment because you don't need to spend time collecting and labeling data. Additionally, they can be used to test and debug your models and data pipelines. The second and most common application is working with custom datasets tailored to your specific domain. Torch Vision offers excellent support for loading, pre-processing, and augmenting your own data. and it makes it easier for you to develop models that address the distinct challenges and requirements of your application. Also, Torch Vision can quickly generate synthetic or fake datasets to help you debug model pipelines, and they ensure that the shape of your data remains consistent for your architecture. In this video, you'll get to know how to work with all of these different types of datasets. Let's start with pre-built datasets. Torch Vision's official documentation includes a comprehensive list of datasets organized by the type of problem they solve, including image classification, which assigns labels to images, object detection, which identifies and localizes objects within an image, segmentation, which classifies pixels to distinguish between object instances, and a whole lot more. Some popular pre-built datasets include FashionMnist, featuring clothing items like shirts, shoes, and bags, SVHN, which contains images of house numbers from Google Street View, CelebA, with celebrity portraits annotated with 40 attributes, like smiling or wearing glasses, plus bounding boxes and facial landmarks. Coco, which includes annotations for over 300,000 images for object detection, segmentation, and image captioning. And there's also Pascal VOC, which has about 3,000 images for object detection and segmentation for over 20 classes. ImageNet deserves special mention here. It's a large-scale dataset with over 1 million high-resolution images across 1,000 categories. It has long been the gold standard for training deep neural networks and testing state-of-the-art models. But just keep in mind, ImageNet requires manual downloading from their website due to its licensing policy. Let's now look at how to load a pre-built dataset like CIFAR, which contains 32 by 32 color images of different object classes. CIFAR 10 and CIFAR 100 have 10 and 100 classes respectively. Here's the code to load CIFAR 10. First, select the root directory for downloading the images. Set train equals to false, and this instructs Torch Vision to download the test set, otherwise it'll use the training set. Setting download equal to true downloads the dataset from the internet, unless of course it's already been downloaded. If you know which transforms you want to apply, you can specify them when initializing the model using the transform argument. Finally, pass the dataset to a data loader to handle batching, shuffling, and parallel data loading during training. Here, the dataset is organized in batches of 8 images and it's shuffled. Keep in mind that test sets are typically not shuffled. It's just done here for educational purposes, so a new image will be displayed each time. This image shows the results from one of those shuffled batches. Note that each dataset is unique, and the loading method into PyTorch may vary. That's why it's crucial to carefully read the documentation from each dataset. For demonstration, let me show you how to load a different dataset, EMNIST, and specifically the subset known as the digit split, which contains 70,000 28 by 28 grayscale images of handwritten digits. Loading this dataset requires an extra parameter compared to CIFAR 10. EMNIST comprises 6 different subsets, or splits, with different images and labels, so you need to specify which one you want to load. And in this case, it's set to digits. You can also apply specific transformations to this dataset. For EMNIST, the transformation pipeline involves rotating the image by 90 degrees, applying a vertical flip, and then normalizing using mean and standard deviation of 0.5. These details do come from the dataset documentation. You can load and preview the dataset using a data loader. This is an example from one of the batches. Remember, not all datasets are structured the same, so you should always check the documentation for required parameters and recommended pre-processing steps to save you time and prevent errors. As mentioned before, a primary application of deep learning models is to work with custom datasets. The Torch Vision package integrates so well with these different types of data. Before loading a custom dataset, make sure that your data is organized in folders by class, as you can see here. And you're going to start with the main root folder. Then you'll create one folder for each class in your dataset. And finally, you'll place the images into their respective folders. Then you can use image folder to load your dataset. This is a generic data loader that infers class labels from folder names, which facilitates loading custom datasets and applying transformations. Once loaded, it's a good idea to display the images for validation. And here's an example of a batch. In many situations, it's necessary to divide a custom dataset into training and testing samples. There are two primary methods for this. One method involves loading the entire dataset and then programmatically splitting it into two sections using functions like random split. The other option is to organize your dataset into two distinct root folders, one for training and another for testing, and then load those separately. Finally, let's take a quick look at how to generate fake datasets. Fake datasets are really useful if you need data to quickly test or debug your pipeline. For example, you may want to confirm that your images are the right size for your model. Torch Vision's fake data class generates random images and labels, mimicking a real dataset's shape and size. This option is ideal for testing without worrying about data availability. As you've seen, Torch Vision provides many options for managing data, including pre-built datasets, support for custom datasets, and synthetic or fake datasets. You can use them depending on your specific objectives, whether you're benchmarking a model, building a task-specific solution, or simply just testing your code. In the next video, you're going to take these datasets and use them to leverage pre-trained models in Torch Vision, and this will help you accelerate your model building and validation. When building a computer vision model, one of the most critical decisions is choosing the right architecture. Over the years, the research community has developed numerous deep learning architectures that excel across various image-related tasks, such as VGG, ResNet, and GoogleNet. Fortunately, Torch Vision offers a comprehensive selection of these architectures through its Models module. These models can be trained from scratch, and many of them have been pre-trained on extensive datasets like ImageNet, which allows you to adapt them to your specific tasks through transfer learning or fine-tuning. Suppose you want to classify an image. You could use a pre-trained model like ResNet 50, which has been trained using the ImageNet dataset encompassing 1,000 classes. The first step is to load the ResNet 50 model along with its pre-trained weights. Setting pre-trained equals true automatically loads weights trained on ImageNet. Switching the model to evaluation mode by calling .eval disables any further training, ensuring that the model is ready for inference. Initially, ResNet 50 provides predictions as numeric indices for 1,000 classes. For models trained on ImageNet, these can be mapped to class labels using a JSON file. By loading this file, you obtain a dictionary that maps each class index to its corresponding label, translating model predictions into actual class names. I'll cover this topic later in this video. The model expects inputs to match the format it was trained on, 224 by 224 pixels, normalized to specific mean and standard deviation values. A pre-processing pipeline handles resizing, center cropping, converting to tensors, and normalization. The unsqueeze function ensures the image is processed as a batch of one, meeting the model's requirements. With the model and input ready, you can now run inference. The model will output raw scores called logits for each of the 1,000 ImageNet classes. These logits are converted to probabilities via the softmax function, scaling each score between 0 and 1, with all probabilities summing up to 1. So, to obtain the model's top 5 guesses, retrieve the top 5 class indices and their probabilities, and map each class index to its name using the ImageNet classes dictionary, which I'll come back to shortly. In this example, the model accurately identified the image as a golden retriever with high confidence, highlighting its effectiveness in object classification. When working with pre-trained models, understanding the classes they recognize is crucial. For example, confirming that golden retriever is a recognizable category before using the model is essential if you want to use the model for that task. There are two ways to extract class names: a manual approach, usually reserved for older models, and a modern approach, where class names are retrieved from the weights object metadata. In the manual method, often used for older models loaded with the pre-trained equals true flag, Torch Vision loads a default set of pre-trained weights based on ImageNet. To determine the number of classes, you can either print the entire model structure, which reveals the final classification layer contains 1,000 classes, or you could directly access this information within the code, which also shows 1,000 classes. Finding that the model contains 1,000 output classes is useful, but it doesn't give you any information on class names, which you would need to retrieve from external sources like PyTorch documentation or helper files. One solution is to download a JSON file that maps indices to class labels from the documentation site. For example, this file shows that index 207 corresponds to a golden retriever. A more efficient approach involves inspecting class names in the weights metadata. To retrieve them, use a helper function to check the metadata and extract class labels. This function is applied both to the model and to its associated weights object. It prints and returns class names and numbers and alerts the user if the information is unavailable. Let me demonstrate this using the DeepLab v3 ResNet50 model designed for image segmentation. This approach involves specifying the model architecture without loading any weights initially. This blank model allows you to select the most current weights available, and it includes metadata about the classes. Then apply the helper function to print out the number of classes and the class names. It reveals that the model was trained to detect 21 segmentation classes. Note that it contains a dog category, which will be used in the lab for segmentation. To summarize, you've seen how to load pre-trained models and weights and apply them to an image classification task. Additionally, you learned 2 different approaches to loading class names. In the next video, you're going to use and adapt these pre-trained models for transfer learning and fine-tuning. When working on computer vision projects such as object detection and image segmentation, being able to visualize your predictions is one of the most valuable tools at your disposal. This is essential because many deep learning models produce complex outputs like bounding boxes or pixel-wise masks. Without visual inspection, you cannot determine if your models are performing correctly. Visualization allows you to catch issues early on, such as incorrect image loading or image augmentations that distort essential features. Further along the pipeline, it enables you to see exactly where your model is making predictions and gauge its confidence in different image regions. This insight is important for diagnosing failures, refining performance, and building trust with end users. Torch Vision offers a wide variety of visualization utilities explicitly designed for these tasks. In this video, I'm going to focus on 2 major utilities, although there may be many others available in the Torch Vision documentation. The 2 I'll focus on are draw bounding boxes for visualizing object detection results and draw segmentation masks, which overlay segmentation masks on images. Let's start with bounding boxes, and this is a key output of object detection models. They will indicate the locations and categories of objects within an image. Visualizing these boxes on the image helps you understand and validate your model's predictions. So let's explore Torch Vision's utility for this purpose. First, we'll import the Utilities module, which contains the Draw Bounding Boxes function. Then, we'll create 2 bounding boxes with coordinates x1, y1, x2, y2, and I'm going to define them as a tensor. In this example, the location of the boxes is hard-coded. Corresponding labels for the boxes can also be defined. Calling Draw Bounding Boxes with the image tensor, box coordinates, and labels results in a new tensor containing the annotated image. And this is the result. This approach is useful for visualizing object detection results, annotating ground truth during dataset creation, and of course comparing predicted versus actual bounding boxes during evaluation. In this example, I manually specified box coordinates for the dog's face and eye. But now I'll show you how to use a pre-trained deep learning model to predict these boxes given a specific label. The model I'm using is Faster or CNN with a ResNet50 FPN backbone. This combination features a Faster or CNN architecture for region proposal and classification, a ResNet50 backbone for feature extraction, and a feature pyramid network to detect objects at multiple scales. It's pre-trained on the COCO dataset, equipping it to detect a wide range of common objects. To use it, load the model and set it to evaluation mode to generate predictions. Before running inference, it's important to know which classes the model can detect. According to the documentation, this model can identify 90 object categories, plus a background class. I can use this helper function that I previously defined to access the metadata and retrieve these categories. And this is the full list of object classes. Be mindful that 10 of these classes are labeled as NA. You can see that car and traffic light are on this class list. Next, I'll load the image of a road. The goal is to draw bounding boxes around all the cars and traffic lights in this image. In the code, I specify car and traffic light as my target classes from the model's categories. I set a red color for bounding boxes around the cars and a blue color for traffic lights. I'll then define the function detect and draw B-boxes, which runs the image through the model, filters the predictions, and overlays bounding boxes on any object matching the target class. The function first converts the image into a tensor. It then processes it through the model and retrieves predictions with bounding box coordinates, class labels, and confidence scores. Predictions are filtered to include only those that match the target object with a confidence threshold above a specified threshold value. I'll use Torch Vision's Draw Bounding Boxes utility to overlay the filtered boxes on the image, customizing line color and thickness for emphasis. Finally, the function returns the image tensor with bounding boxes drawn, or the original image if no target objects were detected above the desired confidence threshold. I can now call detect and draw B-boxes, specifying the model, image path, category indices for the target classes, box colors, and a confidence threshold of 0.7. The resulting image shows red boxes around each detected car and blue boxes around the detected traffic lights. In this case, the model was able to detect all cars in the image, even those in the background, and some of the traffic lights. So you could say it did pretty well considering I used nothing more than the model's pre-trained weights. You'll have a chance to run this code in the lab. Now let's turn to image segmentation. Unlike detection, segmentation does not just draw a box, it returns a mask, and it highlights exact pixels belonging to a class. And this is really useful for tasks like medical image analysis, autonomous driving, or background replacement. I'll show you how to load a pre-trained segmentation model from Torch Vision and use it to draw a mask around the target object, in this case, a dog. I'll use the DeepLab v3 model with a ResNet 50 backbone, pre-trained on a standard segmentation dataset. Start by importing the necessary utilities to draw the segmentation masks and obtain the model from Torch Vision. Load the model with pre-trained weights and set it to evaluation mode. We'll now load the image and apply standard pre-processing, convert it to a tensor, normalize it with ImageNet statistics, and add a batch dimension with unsqueeze 0. This prepares the image to be used as an input to the model. Define the target class name that you want to highlight. In this case, it's just dog, and map it to their corresponding indices in the model's class list. This step generates predictions from the model, producing a 3D tensor where each channel corresponds to a class and each pixel has a class score. Let's extract just the first item from the batch. And then we'll take the argmax over the class dimensions to determine the most likely class for each pixel. And this will result in a 2D tensor of shape height by weight with class indices. We can then create a Boolean mask where each pixel is marked as true if it corresponds to the dog class and false otherwise. The mask will then highlight the dog in the image. Convert the original image to a tensor, scale it to a range 0 to 255, and then convert it to byte format, which is what draw segmentation masks expects. The Boolean mask is unsqueezed to add a batch dimension, the transparency is set with alpha equals 0.5, and the color is set to blue. Finally, display the image using the predefined helper function. The result is a semi-transparent blue overlay highlighting where the model believes the dog is located in the image. This visualization helps you assess segmentation accuracy and is useful for many real-world tasks like background removal, object highlighting, or building interactive user interfaces for selecting image regions. You'll have an opportunity to try this code out for yourself in the lab. And so we've come to the end of this module. By now you've seen how Torch Vision provides a comprehensive suite of tools for working with vision models in PyTorch. You began by exploring what Torch Vision offers, from datasets and model architectures to transforms and visualization tools. You then built pre-processing pipelines that involve normalizing images, applying augmentations, and implementing custom transforms integrated directly into your training loop. You also worked with built-in and custom datasets, structuring your data for seamless integration with PyTorch's data loader. Next, you learned about pre-trained models, how to load them, perform inference, and adapt them to new tasks via transfer learning using examples from both ResNet and MobileNet. Finally, in this video, you explored powerful visualization tools. And these are utility functions that allow overlaying bounding boxes or segmentation masks on your images, helping you to interpret and debug model behavior. Together, these tools empower you to build, train, evaluate, and inspect computer vision models with enhanced clarity and efficiency. In the next lab, you're going to apply these tools in full training loops to train and evaluate models end to end. I'll see you soon. Welcome to Module 3. In the previous module, you focused on working with visual data using Torch Vision. You learned how to pre-process images, use pre-trained models, and visualize predictions such as bounding boxes and segmentations. In this module, the focus will shift to a very different kind of data, text. Working with text data opens the door to some of the most impactful applications in artificial intelligence, from chatbots and virtual assistants to search engines, recommendation systems, and advanced translation tools. When you work with images, data is represented as numerical values such as pixel intensities that are fed directly into neural networks. But with text, things are different. Text is made up of discrete symbols such as letters, words, and punctuation marks. These symbols do not carry intrinsic numeric meaning, so before a model can use them, you have to translate them into numerical representations. A common first step is to assign a unique number to each word, but once text is converted into numbers, it can still behave very differently from other types of data. Unlike tabular data, which has a fixed set of numerical features, or images, which are structured as consistent pixel arrays, text is highly variable. Two sentences might communicate similar ideas, but use entirely different words and structures. In fact, there's rarely one correct way to express an idea in natural language. There are infinite possibilities, and models must be able to handle the variations. Another key challenge is that text is inherently sequential and contextual. Words rarely exist in isolation. Their meaning is determined by the words around them and by the order in which they appear. Take the word bat. If I say a bat flew out of the cave, you know I'm referring to the animal. But if I say he swung the baseball bat, you know I'm referring to sports. This phenomenon, known as polysemy, shows how much meaning depends on context. Understanding context requires more advanced techniques that go beyond simple word lookup tables. And all of this means that NLP workflows require specific steps for processing text, specialized models designed to capture meaning and context, and large data sets and compute power to handle the complexity of language. Let's look more closely at some of the specific reasons why text data is so challenging to work with. First is sequence dependencies and context. Words depend on one another to convey meaning. The phrase baseball bat has a very different meaning from a bat flew, even though they share the same word. Understanding text is not just about understanding individual words, it's also about understanding how those words relate to each other in a sequence. Models that treat each word independently often fail to capture this nuance, which is why modern architectures like transformers are designed to handle contextual relationships in a sequence. Second is variable length and structure. Text comes in different lengths. You might have a single word query in a search engine, or you might have entire paragraphs, documents, or even books. That means that models need to be able to handle sequences of wildly different lengths. In practice, this requires techniques like padding and truncation, which I'll explain in this module. Third is vocabulary and representation challenges. All languages have a massive vocabulary, and it keeps evolving. People invent new words, adopt slang, or use specialized jargon depending on the domain, like medical terminology or legal phrasing. This creates the out-of-vocabulary problem, where a model encounters words that it's never seen before, like a new product name or hashtag. Modern approaches like subword tokenization can help reduce this problem, but it's still a core challenge for natural language processing systems. Finally, ambiguity and polysemy. Words often have multiple meanings depending on context. A bat could be the flying mammal, a piece of sports equipment, or even a verb meaning to hit something. On top of lexical ambiguity, there's also syntactic ambiguity, sentences that can be structured in multiple valid ways, and semantic ambiguity, where the overall meaning of a sentence depends on outside knowledge or context. Humans are really good at resolving these ambiguities effortlessly, but for machines, it's an incredibly difficult task that requires sophisticated language models and often large amounts of training data. Together, these challenges make natural language processing one of the most complex, but also one of the most exciting areas of machine learning. NLP is also one of the most practical fields. It's given us applications that impact our daily lives in ways that you may not even notice. Let's look at 3 areas where NLP plays that central role. First is classification tasks, where the goal is to assign labels to entire pieces of text. Think of sentiment analysis, which helps businesses instantly gauge how customers feel about their products based on reviews or social media posts. Or the spam detection, which filters out unwanted emails before they hit your inbox. Intent classification in chatbots enables a virtual assistant to understand whether you're asking about your account balance or requesting technical help. And there's also topic categorization, where news articles or documents are automatically sorted by subject. The second area is sequence labeling tasks. Instead of labeling a whole sentence, these systems label individual words or spans of text. A great example is named entity recognition, or NER, where models can identify names of people, organizations, locations, addresses, stuff like that. For instance, given a sentence like Alice works at deeplearning.ai in Mountain View, an NER system can pick out Alice as a person, deeplearning.ai as an organization, and Mountain View as a location. This is critical for building search engines, virtual assistants, medical record analyzers, and countless other tools that rely on pulling structured information out of unstructured text. Other tasks, like part-of-speech tagging, where words are labeled as nouns, verbs, or adjectives, are foundational to everything from grammar checkers to speech recognition. And then finally, there are generative tasks. These focus on producing new text from an input. This area includes text summarization, which condenses long reports or articles into a few key sentences. Dialogue generation powers chatbots and virtual assistants that can hold natural conversations. Machine translation has completely changed how we communicate across languages, enabling real-time translation in video conferences or travel apps. And beyond that, you even see models doing creative writing, generating poetry, scripts, or stories. These models can predict one word at a time, carefully building out entire sentences and paragraphs, and which is why they can adapt to so many uses. Taken together, these areas show just how versatile NLP has become, powering everything from how you get information to how you communicate to how businesses can operate at scale. So how does PyTorch fit into all of this? Well, over the last decade, NLP has evolved dramatically. Early systems were based on hand-engineered features and rules, but today's NLP is driven by deep learning. Modern models learn to represent and reason language in ways that generalize to new inputs. PyTorch has emerged as one of the most popular frameworks for building these very models. With PyTorch, you can handle every stage of an NLP workflow. It provides utilities for pre-processing text, converting it into numerical tensors, and building models tailored for language tasks. PyTorch also makes it straightforward to experiment with different architectures, whether you're working with a simple embedding-based classifier or a large-scale transformer model. Historically, PyTorch had a dedicated library called TorchText to simplify NLP pipelines. TorchText provided ready-to-use datasets, tokenizers, and iterators for text processing. However, TorchText is no longer actively maintained. So the current approach is to use PyTorch's core capabilities directly, or to integrate with specialized tokenization libraries and pre-trained model hubs like Hugging Face. This shift gives you more flexibility and ensures that your code is aligned with where the NLP ecosystem is headed. So whether you're building a sentiment analysis tool, designing a chatbot, or experimenting with text generation, PyTorch gives you a powerful foundation. In this module, you'll process text data, create embeddings, and train models using PyTorch. In the next videos, you're going to dive into those PyTorch tools, starting with one of the most fundamental tasks in NLP, tokenization. And that's turning raw text into a numerical form that deep learning models can understand. Images are naturally represented in a format that computers can process, such as arrays of numbers reflecting pixel intensities. But text is different. A sentence is just a sequence of symbols that are meaningless to a machine until they're translated into numbers. And this is where tokenization plays a critical role. In this video, you're going to learn about one of the first steps in NLP, and that's breaking text into smaller units known as tokens, whether they're characters, words, or intermediary elements, and how these units build a foundation for everything else in natural language processing. You'll also discover how to construct vocabularies, assign numerical indices, and manage special tokens that models may depend on to interpret sentences. What exactly is tokenization? Tokenization involves taking a raw text and dividing it into tokens, distinct units that a model can process and learn from. Depending on the task, tokens can represent words, which are often used in NLP tasks like sentiment analysis or document classification. Subwords, which more advanced tokenizers use to manage rare or novel words that the model may not have encountered before. And characters, which are the smallest units of text suited for certain languages or scenarios. Let's dive into these, starting with character tokenization. Character tokenization breaks text into individual characters. For example, tokenizing the word silent, the character level yields S-I-L-E-N and T. Similarly, the word listen becomes L-I-S-T-E-N. Both words comprise the same characters, rearranged, making them anagrams. This poses a risk that without a specified token sequence, both tokenized words would appear identical to a model. Character tokenization is useful for languages with intricate word structures or for avoiding that out-of-vocabulary problem, since every character will always belong to your vocab. Computers typically handle characters using numeric encodings like ASCII, where each character, such as uppercase A, has a number assigned, like 65. Although this method translates symbols to numbers, doesn't capture meaning. Let's move on to word tokenization. Here, a sentence is divided into individual words. For languages like English, it's often effective to split by spaces or punctuation. For example, the sentence, "I love my dog," could be tokenized into I, love, my, and dog. These 4 tokens represent 4 unique words. Since machines don't understand words like dog or love, you'd map each unique word to an integer index. For example, you can map I to 1, love to 2, my to 3, and dog to 4. This mapping allows you to represent a sentence as a sequence of numbers. And while they can be directly input into NLP models, you'll explore how to convert them into embeddings in a later video. And an embedding is a more suitable numerical representation of words that can capture meaning as well as the relationships between words. It's also common to include special tokens, such as UNK for unknown words, pad for sequence padding, and sometimes start and end to mark sequence boundaries. Also, modern NLP libraries, such as those powering models like BERT, which we'll discuss later in this module, will use CLS for classification inputs and SEP for segment separation. Some challenges with word tokenization include vocab size. Should you include every word that you've ever encountered? Large vocabularies contain millions of words. Therefore, a typical solution is to limit the vocabulary to the top number of words, maybe the 50,000 most frequent, and then map the rest to the UNK token. Text normalization is another challenge. Should dog with an uppercase D and dog with a lowercase d be treated as the same token? What about punctuation, contractions, or misspellings? Pre-processing often includes steps like lowercasing, removing punctuation, and handling contractions, like turning don't into do not. Here's a basic Python function to tokenize text and build a vocabulary from scratch. You'll start with two sentences. I love my dog and I love my cat. You define a tokenize function to convert a string to lowercase and then split it into words based on whitespace. Then create a build vocab function that maps each unique word to a numerical ID. Next, you tokenized each sentence. Iterate through each token or word and add it to the vocab if it's not already present. And then you can assign it a unique integer ID. Calling build vocab on both sentences results in a word tokenized version where each unique word gets its numerical index. In real NLP pipelines, sentences often vary in length. You might get both a brief tweet and an extensive product review in the same dataset. Yet neural networks actually require fixed size inputs. The simplest solution to this is padding and truncation. Padding involves appending pad tokens to shorter sequences to match the length of the longest sequence in the batch. Truncation, on the other hand, cuts long sequences to stay within a maximum length, preventing excessive memory or computation usage. For example, given the sentences I love my dog and I love with a fixed sequence length of 4, you would pad the latter of these with 2 pad tokens. Conversely, if the maximum length is 2, you truncate I love my dog to just I love. Both padding and truncation standardize each sequence's length, enabling you to stack them into one tensor for processing. However, padding has its downsides. For example, if one sentence is particularly long, padding others to match it can waste memory and computation on lots of meaningless tokens. A better approach could be bucketing, which involves grouping similar length sequences to reduce padding overhead. Or you could apply smart truncation policies that preserve vital parts of long sequences instead of just cutting arbitrarily. Since padding tokens lack real-world meaning, models use attention masks to differentiate them. And these are binary tensors that indicate which tokens are actual words and which ones are merely padding. For I love with 2 pad tokens, the mask would be 1, 1, 0, 0, where ones indicate actual words and zeros mark padding to be ignored. You would use both tokens and masks as inputs to models. In this video, you reviewed the basics of tokenization and how combining padding, attention masking, and efficient batching strategies like bucketing enables you to effectively process text of varying lengths without wasting memory or reducing model performance. In the next video, I'm going to demonstrate how to leverage a pre-trained tokenizer to automate the tokenization process. Building a tokenizer from scratch can be educational, but it's not always the most efficient method. Modern NLP workflows often rely on tokenizers that come pre-trained on massive text corpora combined with powerful models. In this video, you're going to explore Hugging Face, a platform that provides access to state-of-the-art tools for text processing. You'll learn how to use a pre-trained tokenizer from BERT, which automatically handles subword splitting, special tokens, and a whole lot more, turning raw text into model-ready input in just a few lines of code. Before diving in, let me introduce you to Hugging Face. Hugging Face was originally a chatbot company, but it has evolved into a leading hub for NLP and machine learning models, currently serving as an open-source community and platform for sharing models, tokenizers, and datasets. The Hugging Face ecosystem allows you to access cutting-edge models and tools, making it a one-stop shop for NLP tasks like text classification, translation, and summarization. Instead of creating a custom tokenizer or training a model from scratch, you can leverage these pre-trained components, which will save you time and allow you to focus on solving the actual problem at hand. Hugging Face also facilitates collaboration and contribution. You can upload your models or your datasets to the hub, share them, and version them as you would with code on GitHub. In this module, you'll be working with one of Hugging Face's most popular models, BERT. BERT is short for Bidirectional Encoder Representations from Transformers, and it's a pre-trained language model introduced by Google. Its power comes from reading text bidirectionally, considering both left and right context of each word for deeper understanding. It was trained on massive text data sets like English Wikipedia and Books Corpus. I'll go back to BERT in a later video. To use BERT, the input text must be formatted in a very specific way. Unfortunately, the pre-trained tokenizers can handle all of this for you. The BERT tokenizer is designed to format input text for the BERT model. It splits words into subword tokens using word piece tokenization, which handles rare or unknown words by breaking them into smaller, more frequent parts. It also adds special tokens like CLS at the start and SEP at the end of an input sequence. Each token is then converted into an index using the tokenizer's vocab, which results in a numerical input tensor suited for the BERT model. The BERT tokenizer guarantees your inputs are formatted as BERT expects. And here's the code to accomplish this. Let's break it down. First, begin by importing BERT tokenizer fast from Hugging Face's Transformers library. Then, initialize the tokenizer, which can be loaded from a local directory or directly from Hugging Face's servers with BERT base uncased. And this will provide you with an out-of-the-box tokenizer. Next, you're going to pass your sentences to the tokenizer. Set padding to true to ensure that all sequences are of equal length by adding padding tokens as needed. Truncation equals true ensures that sentences longer than the model's maximum will be trimmed. And then by setting return tensors to PT, we're going to return pytorch tensors ready for model input. The tokenizer's output includes input IDs, which are the numerical representations of your text, and you can convert these ITs back into tokens using BERT's built-in function. The tokenizer also provides access to its entire vocabulary via getVocab, allowing you to inspect or analyze how words are represented. Finally, you can print the resulting tokens and their IDs. This will help you understand how the tokenizer splits text, handles casing, and inserts special tokens. The output is a dictionary which maps each BERT vocab token to a unique integer ID. This complete pre-processing pipeline splits sentences into subword tokens, converts them to IDs, pads them to the same length, and returns them as tensors, all in a few lines of code. And you're going to practice this in the upcoming lab. In this video, you've seen how to leverage Hugging Face and BERT's tokenizer. Using pre-trained tokenizers ensures that your text aligns with the expectation of the BERT model while avoiding the pitfalls of manual vocab building. You learned how special tokens like CLS and SEP are added and how each word is split and indexed according to the model's rules. In the next video, you're going to complete this process by turning these tokenized outputs into tensors that models can then use for training or prediction. Now that you're familiar with text tokenization, the next step in preparing these tokens for a neural network is to convert them to a numerical format through a process called tensorization. In NLP, tensors typically represent batches of text. A 1D tensor might hold a tokenized sequence for one sentence, a 2D tensor could represent multiple sentences, and a 3D tensor might capture complex relationships across different sentences. Take, for example, this tokenized sentence, I love my dog, with IDs 1 for I, 2 for love, 3 for my, and 4 for dog. And this can become a 1D tensor containing the sequence 1, 2, 3, 4. With a batch of 3 sentences, you could now create a 2D tensor where each row represents a sentence in numerical form. And PyTorch is very efficient at handling these tensors. There are also various ways to represent individual words within a model. One of the simplest is called one-hot encoding, where each word in the vocab is represented by a long vector filled with zeros, except for a 1 at the position corresponding to the word. For instance, in this vocab of 5 words, dog is the 4th item, so its one-hot vector would be 0, 0, 0, 1, 0. Now this method works for small vocabularies, but it doesn't scale well. A vocab with 50,000 words would require vectors with 50,000 elements, each with only one non-zero value, and that's a big waste of space. One variation of this idea is the bag of words approach. Here, a sentence is represented as a vector of frequencies, where each position stores how many times that word appears in the text. A key limitation is that bag of words ignores word order. For example, the vectors for I love my cat and my cat I love are identical in this representation, given that both phrases use the same words with a count of 1 for each word. Another approach is term frequency inverse document frequency, TF-IDF. Term frequency measures how often a word appears in the document, while inverse document frequency downweighs terms that appear in many documents. Multiplying DF by IDF gives a higher weight to terms that are frequent in a given document but rare across the corpus. In this example, the words I, love, and my, which are very common, would carry a TF-IDF of 0, while less frequent terms like dog and cat will have higher values. Like bag of words, TF-IDF is order agnostic, but it does a much better job at handling informative words. These approaches create large, high-dimensional vectors, leading to massive memory usage without capturing context or semantic information. Historically, they've been useful, but they're now giving way to more sophisticated methods. A more modern and efficient technique is the use of embeddings, which capture contextual and semantic connections between words and present compact vectors. We'll explore embeddings in detail in the next video. But for now, remember that tensorization is that process of taking tokenized text, mapped to numerical IDs, and converting that to tensors ready for processing in neural networks. In previous videos, you saw how tokenization assigns numerical IDs to words or characters, essentially converting text into a format that neural networks can process. However, these numbers only act as identifiers without any inherent meaning. For instance, mapping cat to 4937 and dog to 3899 merely provides labels. There's nothing in those numbers that reveals that cat and dog share semantic similarities, like they're both pets, and how they're more similar to each other than they would be to, for example, a banana. This leads us to word embeddings, a significant breakthrough in natural language processing. Embeddings represent each word as a vector in a continuous high-dimensional space. The objective is to position vectors so that semantically related words are closer together, while unrelated words are further apart. Think of it as constructing a map of meaning. Rather than treating every word as an isolated symbol, embeddings allow models to understand relationships. See, for example, these words in a two-dimensional space. Synonyms like happy and joyful end up with almost overlapping vectors, whereas antonyms like hot and cold are further apart but remain relatively close because they share a conceptual domain, temperature. This approach allows models to infer word relationships from their numerical vectors. Knowing that happy and joyful are similar helps in generalizing to new sentences. These relationships are learned directly from the data, and they can capture complex relationships that are challenging to define manually. Embeddings enable modern NLP models to represent text meanings beyond just simple ID or one-hot vectors. To illustrate the power of embeddings, consider words like king, queen, prince, and princess. Using one-hot vectors, each word becomes an isolated vector of zeros with a single one at a unique position. That offers no insight into how these words are related to each other. With embeddings, each word occupies a position in a continuous high-dimensional space. It's a map of meaning. Through visualizations, we can simplify this to 2D or 3D plots, and these vectors will often have hundreds of dimensions, revealing those complex semantic relationships. But in this simplified plot, words will appear as points in a 3D space, with axes representing the concepts of gender, royalty, and age. Man and woman align along the adult and non-royalty axes, differing by gender. King and queen share age and royalty, but differ by gender. Prince and princess are their younger counterparts, and boy and girl are parallel to man and woman, reflecting youth. Embeddings capture similarity and relationships. They learn by observing how often words appear together to encode abstract concepts like gender and age with no manual intervention. For example, subtracting the man vector from king will give you a vector representing royalty minus male. Adding the woman vector moves you towards the female concept, and that will land you near to the queen vector. With embeddings, vectors can even be added or subtracted component-wise. Let's say these 4 words are represented by the following 3D vectors. King minus man would result in this vector. Adding woman gives this vector, which is much closer to the vector for queen. You can see how embeddings are useful for representing these word relationships and the complex concepts around them in mathematical terms. The power of embeddings derives from the distributional hypothesis. Words appearing in similar contexts often have similar meanings. In a plot, embeddings for words like roses, lilies, and tulips will be very close to each other, but they'll be further away from the cluster containing apples, bananas, and mangoes. Hierarchical relationships are also expressed, like how dog is close to animal, and even analogies like the king minus man plus woman equals queen, example that I just explained. Embeddings offer a way to measure word similarity in mathematical terms. If you imagine words as coordinates in a multidimensional space, for example, of 300 dimensions rather than just 2 or 3, then you can start to compare words using cosine similarity. And this involves measuring the cosine of the angle between the vectors. A cosine similarity of 1 indicates that both vectors point in exactly the same direction. 0 means that they're orthogonal or unrelated, and -1 means they point in opposite directions. So king and queen would have a high cosine similarity because their vectors are almost parallel, reflecting similar semantic roles. Meanwhile, king and girl will have a much lower cosine similarity because they point in completely different directions, which is in line with their having very little semantic connection. In PyTorch, embeddings are implemented through an embedding layer, which basically acts as a lookup table that maps token IDs to dense vectors. These vectors are then learned during training and are adapted to your specific task. The process to create embeddings typically begins by assigning integer IDs to words, which are then one-hot encoded. The embedding layer then turns these indices into dense vectors in a smaller dimensional space, reducing the input dimensions to try to capture the semantic meaning. Embeddings can then be fed into neural networks for tasks like classification or translation. Before models like BERT and GPT, words were often represented with static embeddings, where each word in the vocab matched a fixed vector regardless of context. So the word bat had the same vector whether it referred to the animal or a baseball bat. Well-known static embedding models include Word2Vec, Glove, and FastText. These models produce embeddings that convey rich semantic information on word similarity, clustering related items like apple, orange, and banana, but they can't account for polysemy, words with multiple meanings. That limitation led to contextual embeddings, also known as dynamic embeddings, which adjust a word's vector based on context. For instance, bat would yield distinct vectors in the phrase flying bat versus baseball bat. Dynamic embeddings have been popularized by models like BERT, GPT, and Elmo, and they use deep neural networks to assess entire sequences and compute embeddings that incorporate information on surrounding words. The advantage is that they deliver much more nuanced language representation, and they are great for tasks that demand subtle meaning distinctions, like sentiment analysis, named entity recognition, or machine translation. The drawback is that they are computationally intense because they require recalculating embeddings for every sentence processed. To summarize, word embeddings are an important leap from raw text to rich, meaningful, numeric representations of words. They capture meaning, context, and semantic relationships in compact, trainable vectors. In the next video, you'll get some hands-on experience with embeddings, both static and contextual, You'll implement them in PyTorch, visualize them, and tackle practical challenges using text data. In the previous video, you learned about the power of embeddings in capturing the meaning of text. Now it's time to see them in action. In this video, you'll implement two types of embeddings: static embeddings using Glove and contextual embeddings using BERT. You'll load these pre-trained embeddings into PyTorch, use them to represent text, and visualize how they arrange words in space. Let's begin with Glove, and this is short for Global Vectors for Word Representation. Glove is a popular static embedding model trained on a massive text corpus, learning from how often words will appear together. You'll use the Glove 6b dataset, trained on a mixture of Wikipedia and GigaWord data, comprising of 6 billion tokens and featuring 400,000 unique words. To get started, download the Glove dataset and load the model. In the lab, this can be done with a helper function. Specify the file path and load the model, which uses a 100-dimensional vector to represent each token. Next, define a function to calculate the cosine similarity between a target word and all other words in the vocab so you can find the closest semantic matches. This function begins by filtering out any words you'd like to exclude from the search. This prevents including your input words in the result. You then build an embedding matrix with the remaining words and compute cosine similarity between the target and all other words. Finally, you can return the top n closest words along with their similarity scores. Let's test Glove's ability to solve the classic king minus man plus woman analogy using a function that you've just created. First, we'll confirm that these words are present in the model's vocabulary and we'll extract their embeddings. Then, we'll compute the result of the analogy by subtracting man from king and adding woman, and then pass the result into the find closest word function. In this example, the output you'll see is king minus man plus woman approximates queen. You can see that queen got the highest cosine similarity score, and the runners-up were things like monarch, throne, daughter, and prince. This demonstrates how embeddings can encode both meaning and relationships, showing analogical reasoning. Static embeddings like Glove, which provide each vocab word with a single fixed vector, are excellent for many tasks. They're fast and efficient, but they have a key limitation. They can't distinguish words with multiple meanings, known as polysemy. For example, the word bat will get the same embedding regardless of whether it refers to the animal, as in a bat flew out of the cave, or to a piece of sports equipment, as in he swung the baseball bat. You can verify this with Glove by retrieving the vector for bat in both sentences. You can then compare their embeddings to see if they match. And as expected, both embeddings are identical, indicating that Glove assigns the same representation for both contexts. This occurs because static embedding models like Glove will average all contexts in which a word appears during training. In contrast, BERT provides context-dependent embeddings, and it adjusts the vectors based on the surrounding words. Let's give BERT a try. First, we'll load BERT and its tokenizer using a predefined helper function. Then, we'll tokenize and encode the sentence, a bat flew out of the cave, and we'll process it through BERT to extract the resulting contextual embeddings. Next, we'll extract tokens from their IDs, and then we'll repeat the process for this phrase, he swung the baseball bat. Finally, we'll compare BERT's vectors for bat in both sentences, and you'll find that they're different, demonstrating BERT's ability to differentiate between the animal and the sports equipment by generating context-specific embeddings. So when would you use static and when would you use dynamic embeddings? Static embeddings like Glove are ideal for simpler tasks, such as topic classification, where speed and memory efficiency are key. Contextual embeddings like BERT are better for advanced tasks, such as question answering, chatbots, or summarization, where a nuanced understanding of word meaning is required. If the meaning heavily depends on context and you have resources available, BERT is the better choice. Otherwise, static embeddings will often suffice. Visualizing embeddings is a great way to understand their behavior. Word embeddings occupy high-dimensional spaces, usually more than 100 dimensions. Since hundreds of dimensions aren't directly visualizable, dimensionality reduction techniques can be used to project these vectors into a 2D or 3D space. Two popular techniques are PCA, which is Principal Component Analysis, and this finds directions of maximum variance to project the data, although it might distort local relationships. And the other is TSNE, which is T-distributed stochastic neighbor embedding, and this maintains local structure and creates intuitive visual clusters, but it's much more computationally intensive. I'm not going to cover these techniques in detail in this course, but you should definitely do some more research on your own if you're interested in word embedding visualization. After applying dimensionality reduction, you can then plot word embeddings to uncover natural word clusters, such as roses, lilies, and tulips forming one cluster, while apples, bananas, and mangoes cluster separately. These formations highlight semantic similarity. Words from similar linguistic context will appear close to each other in the embedding space. Take a look at this example plot showing clusters for book titles and their genres. Notice how Don Quixote and Jane Eyre are near each other in the fictional novel category, and they're somewhat distant from The Wonderful Wizard of Oz in the fantasy cluster, and even further away from Encyclopedia Britannica, located in the non-fiction cluster. And here's some code to visualize embeddings using PCA in Python. First, you'll select a small set of words across the semantic categories of vehicles, pets, and fruits. You'll retrieve each word's glove vector and convert it to a NumPy array. And then you'll use PCA to compress the original 100-dimensional vectors to 2 dimensions, allowing for easy plotting. In the output, you can see how all of the vehicles cluster together, as well as all of the pets and all of the fruits. You can visually verify that glove embeddings capture meaning by grouping related concepts in vector space. Keep in mind that when you reduce high-dimensional data to 2D or 3D, some information might get lost. PCA may distort less important dimensional distances, while TSNE could exaggerate cluster separation. Nevertheless, visualization is a powerful sanity check to determine if the embeddings work as expected. When using embeddings in real projects, remember a few key points. First, remember the implications of dimensionality. Higher dimensions capture richer semantic relationships, but require more data, computation, and of course memory. Standard word embeddings can exceed 100 dimensions. Next, select the form of initialization you'll use. You can initialize embeddings randomly and train them from scratch, or you can use pre-trained embeddings like glove or fast text, and then either freeze or fine-tune them to your specific task. Pre-trained embeddings can really speed up training and boost performance, particularly when data is limited. You should also decide how to handle the out-of-vocab OOV problem, what to do when your model encounters new words that it previously hasn't seen. Solutions may include using subword models like fast text or reserving a UNK unknown token for unknown words. Finally, consider your task requirements. For rapid prototyping or limited context tasks, static embeddings will do. But for more complex tasks like machine translation or question answering, you'll benefit from BERT or GPT's contextual embeddings. To summarize, embeddings convert discrete words into continuous vectors. They capture subtle semantic relationships and enable models to work meaningfully with language. Static embeddings provide a fast initial representation, while contextual embeddings handle nuance and ambiguity for deeper language comprehension. In the next video, you're going to take this concept a step further by building a text classification model using embeddings as input representation and illustrating how these vectors integrate into real neural networks for NLP tasks. Text classification is integral to many everyday applications. When your inbox filters an email as spam or not spam, or a social media platform determines the sentiment of a post as positive or negative, text classification is at work. In this video, you're going to build a text classifier from scratch using pytorch. The process is very straightforward. Convert words to tensors, aggregate the tensors, and let the model decide if you're writing a love letter or an angry complaint about your Wi-Fi. At its core, a text classification pipeline involves 3 steps: embedding, pooling, and prediction with an output layer. These steps are foundational to many state-of-the-art systems. The first step involves representing words numerically to capture their meaning. Each token, typically a word or a subword, is mapped to a vector of real numbers via an embedding layer. These embeddings are learned during training as the model determines where each word should be placed in vector space to solve the classification task. In step 2, a pooling layer aggregates the tensors of multiple tokens into one. Many pooling methods can be applied. For example, mean pooling averages all word embeddings, giving equal weight to each word, and this works really well when all words contribute to the sentence's meaning. Max pooling takes the maximum value in each dimension, emphasizing the most dominant features, and sum pooling adds embeddings together, which can preserve frequency information. Choosing the best pooling model depends on your task. And that said, mean pooling is a common starting point due to its simplicity and stability. Once the sequence is reduced to a single vector, the final step is mapping it to task-specific outputs, using a fully connected layer that outputs a score for each class. A softmax or sigmoid function is applied to convert these scores into interpretable probabilities. This three-step approach is effective and serves as a solid baseline before exploring more complex approaches like recurrent neural networks, or RNNs, long short-term memory, LSTMs, or of course transformers. While pytorch allows you to create separate embedding and pooling layers manually, it also offers a shortcut with nn.embeddingbag, and this performs embedding and pooling in a single line of code. This matters for two reasons. First, performance. It avoids generating intermediate tensors for every token embedding in large text batches, and this saves memory and compute resources. And then secondly, of course, is simplicity. It eliminates the need for custom pooling logic, and it features built-in modes like mean and sum for easy selection. To use embedding bag, you feed a batch of token IDs with an offset tensor, and that marks the start of each sentence. Internally, embedding bag looks up embeddings and pools them based on your chosen mode, returning a fixed size vector per sentence. This approach is well suited for text classification because it efficiently handles variable length sentences and produces a compact vector for prediction. Before building the model, you need to pre-process the data by selecting and loading the dataset. You clean and tokenize the text, and then you split it into training and validation sets before finally building vocabularies for each. Then data loaders will efficiently handle batching and shuffling during training. In the lab, you'll use the food.com recipes and user interactions dataset, which is made up of thousands of cooking recipes. Specifically, you'll work with a subset of recipes that are either fruit-based, such as apple-a-day milkshake, or vegetable-based, such as zuppa toscana. Your goal is to build a text classifier to label recipe titles as either fruit or vegetable. With the data ready, you're going to test 4 different models: embedding bag with mean pooling, and manual embedding with mean, max, and sum pooling. Conceptually, these models share that same pipeline: embedding, pooling, and output. The first model, built using embedding bag, combines embedding and pooling into one efficient operation, and the init method features 3 layers. The nn.embeddingbag layer receives a batch of token IDs and offsets and computes a fixed size vector for each input. This layer performs embedding and pooling at once without manually looking up embeddings and then computing an average or sum. Next is dropout layer, which helps prevent overfitting by randomly zeroing half of the elements during training. And then finally, a fully connected layer maps the pooled embedding vector to raw scores for each class. The forward method defines how input flows through the model. It calculates pooled embeddings, applies dropout, and passes the result through the fully connected layer to generate class legits. The second model relies on manual pooling, sharing the same conceptual pipeline. This class begins with a standard embedding layer that converts token IDs into dense vectors. Setting the padding IDX parameter to 0 ensures that padding tokens will not affect training. The pooling argument specifies how sequence embeddings will combine in the pooling layer. The model also features a fully connected layer for classification and a dropout layer for regularization. The forward method uses a mask to filter out the padding tokens and then applies the chosen pooling strategy to the remaining tokens. For mean pooling, it sums embeddings and divides by the valid token count. For max pooling, it identifies the element-wise maximum, and for sum pooling, it adds all token embeddings together. After pooling, the model applies dropout and sends the result through the fully connected layer, which outputs class legits. Once class definitions are set, models are ready to be initialized. And here's how that looks. The vocab size parameter specifies the number of unique vocabulary words. Embedding dim is a hyperparameter that controls each embedding's vector size, and num classes represents potential outputs. In this case, there's two, fruit and vegetable. These parameters apply to all model versions. Once the models are created, they're ready for training and evaluation. In this video, you crafted a baseline model that will be trained from scratch. Next, you'll create and train these text classifier models in the lab, and you'll compare the embedding and pooling strategy performance. Which model do you think will work best? Welcome to Module 4. In the last two modules, you focused on handling different types of data, images with torch vision, and then text using Hugging Face tools. Now you're going to shift gears to focus on training models efficiently. Training a model can consume a lot of time and memory, but the solution isn't always to upgrade your hardware. This module will teach you how to optimize training time and memory usage while also maintaining good model performance. You'll learn how to build efficient data pipelines, profile training loops to identify bottlenecks, and apply practical optimization techniques to make models run faster and use memory more efficiently without buying additional hardware. In this video, the focus is on the first point, building efficient data pipelines. Imagine you've developed a model, but training is painfully slow. The immediate response might be to invest in a more powerful GPU or hardware. While this solution can be effective at times, it's worth exploring more cost-effective strategies like addressing data bottlenecks. To grasp the impact of data bottlenecks, let's visualize what happens behind the scenes. Imagine a pipeline where data flows from storage through the CPU and finally to the GPU, which accelerates model training. Ideally, the pipeline should be wide open, with batches arriving as fast as your model can process them. But that's rarely the case at first. Often, your GPU might be capable of processing, let's say, 10 training examples at once, but your data loader can only supply 2 at a time. In such cases, simply boosting the GPU power won't solve the issue. The goal is to load samples faster to ensure that the accelerator operates at full capacity. And this allows for more experiments, quicker feedback, and reduced training time. In this and in the next video, you'll learn how to alleviate bottlenecks using efficient data loading techniques. Let's review two main PyTorch tools for loading data, the dataset class and the data loader. The dataset class is the blueprint for your data. It tells PyTorch how to load and return one sample at a time. A custom dataset is implemented using 3 essential methods. Init sets up or loads the data, len returns the total number of examples, and getItem retrieves a single item by index. Once defined, you can pass this dataset to a data loader, which will then manage batching, shuffling, and parallel loading. In the data loader, you first must define the number of samples per batch. Shuffle equals true randomizes data in every epoch, preventing the model from memorizing the order of the data, and this helps avoid overfitting. Num workers tells PyTorch how many CPU workers will load data in parallel. This video focuses on how that number of workers can affect data pipeline efficiency, and the next video will explore the other parameters. The number of workers is a key parameter for optimizing data pipelines. It controls how many CPU processes run in parallel for data loading. By default, the PyTorch data loader uses 0 workers, meaning a single process loads data. And this becomes a bottleneck when a powerful GPU sits idle, waiting for the next batch. It's like having a single cook in a busy restaurant. Even if they're skilled, one cook can only support a limited number of orders. And if we add more cooks, more orders are fulfilled, and the restaurant can run more efficiently. More workers in your data pipeline mean multiple CPU workers preparing data in parallel, and the GPU will rarely wait. To understand the impact of this parameter, here's an experiment using the CFAR10 dataset and comparing several numbers of workers. This loop tests how long it takes to load data for one epoch with 0 through 10 workers, repeating each test across 5 epochs. The first 2 epochs will warm up the system, while the last 3 will be averaged to provide a stable measurement. You create a data loader for each worker setting and measure data loading time per epoch while handling potential errors. Finally, you'll clean up the memory. Once the data is collected, results are visualized in this graph, displaying the average epoch time in milliseconds based on the number of workers. The average epoch time indicates the training speed, which is the main concern here. You'll notice that initially increasing the number of workers reduced training time. Going from 0 to 2 workers showed a noticeable improvement. Beyond 2, the gains plateaued. Adding workers will help us up to a point, but managing many processes eventually outweighs the benefits, as each worker does consume resources. Too many workers will compete for the CPU, memory, and disk I/O, and that can slow the progress. Returning to the kitchen analogy, 2 or 3 cooks might optimize your kitchen, but adding many more could cause them to start competing for resources, and this leads to confusion. It's important to note that these results are not universal. They will be different by dataset, model architecture, and hardware. Performance may also fluctuate with every run on this online platform, and that's to be expected due to some unpredictability in resource allocation from the server. These variations are normal, so it's important to focus on interpreting trends instead of absolute values. As a rule of thumb, a good starting point for the number of workers is to find your machine's physical CPU core count and experiment from there to find the saturation point. So what drives this pattern? Efficient GPU usage significantly influences training speed. If the GPU is idle waiting for CPU data delivery, training slows down. Keeping the GPU busy yields faster and better results. This other graph illustrates GPU usage efficiency for different numbers of worker values. The blue bar shows active GPU processing time, and the yellow bar indicates idle time. Notice the trend, increasing from 0 to 4 workers steadily improves GPU efficiency. Beyond 6 workers, efficiency stalls. This aligns with the previous findings of diminishing returns beyond 2 workers, partly due to inconsistent GPU use. So before upgrading your GPU, remember it's not just about hardware, it's also about usage. While important, GPU usage is not the only factor. CPU, memory, and disk I/O will all affect training time too. And the advantage of GPU activity is that it's directly measurable and optimizable. Start by measuring average epoch time, the key metric. Then break it down to understand performance drivers, such as GPU usage. This analysis will help you pinpoint bottlenecks and refine your settings. And remember, experimental results will vary based on your setup, so focus on that analytical process, running experiments, observing trends, and learning to interpret data to make insightful decisions. This experiment underscores a core principle. It's not about maximizing the number of workers, but about finding the optimal number to consistently feed the GPU without overwhelming the system. In the next video, you're going to explore how batch size and other advanced data loader settings can influence training performance. In this video, you'll explore 2 techniques to optimize memory usage: mixed precision and gradient accumulation. These methods often work together, allowing you to train larger, more complex models without changing your hardware. Most deep learning models use 32-bit floating point numbers during training. Mixed precision training combines both 16-bit, which is half precision, and 32-bit, which is single precision, floating point numbers. Essentially, the model relies on float 16 precision where possible and defaults to float 32 precision when needed for stability, and this reduces memory usage while maintaining accuracy. Gradient accumulation, on the other hand, increases the effective batch size during training without exceeding memory limits. Typically, a model updates weights after every mini-batch. With gradient accumulation, several mini-batches are processed sequentially without immediate weight updates. The gradients are stored and summed over a specified number of steps, known as the accumulation step. Before applying these techniques, you'll need to define some key utilities. a custom callback to measure peak memory usage and throughput, a training function to encapsulate the training logic and run optimization experiments, a run optimization function to tie everything together, such as initializing the model, trainer, and the dataset, executing the training, and gathering results. The full code will be available in the lab after this video for a detailed review. You'll conduct an experiment testing 6 configurations that combine gradient accumulation and mixed precision, examining their impacts on memory usage and accuracy as detailed in this table. Start with a baseline or standard model using 32-bit precision with no advanced optimizations. Then try a version with mixed precision. For gradient accumulation, you'll test 2 setups. The first one will have a gradient accumulation step of 2 and a batch size of 128. Multiply these 2 numbers together to get the effective batch size, which is then 256. The second one will have a gradient accumulation step of 4 and a batch size of 64, which maintains the effective batch size of 256. Finally, you'll test a configuration combining both mixed precision and gradient accumulation, again with an effective batch size of 256. Maintaining an effective batch size of 256 allows for direct comparison, ensuring that every configuration processes the same number of training examples per optimizer step. Here's the implementation for gradient accumulation with a per step batch size of 128 and an effective batch size of 256. First, set the batch size to 128 and create a CFAR10 data module with this value. Then define the target effective batch size of 256. Calculate the number of mini batches needed before a weight update by dividing the effective batch size by the actual batch size. Here, 256 divided by 128 equals 2, which is what you will use for the grad accum variable. This means that gradients will accumulate over 2 forward or backward passes before a single optimizer step. Next, run the run optimization function with this setup. Set the precision to 32 true for standard 32-bit precision, and pass the grad accum value, the data module, and the number of training epochs. Finally, collect the results. Other configurations follow the same structure with updates to the batch size, precision, and grad accum. After applying these optimizations, you can examine how they performed in terms of 2 key metrics. The first is validation accuracy, which is the model's performance on the validation dataset post-training. The second is peak GPU memory usage during training, which is an indicator of resource efficiency. This bar chart displays validation accuracy for each of the 6 models. Notice how the results are stable across all techniques. The standard 32-bit model achieves 72%, and other configurations are within 1% of this value. Interestingly, combining both techniques yields the highest accuracy, but the differences are minor. The takeaway? Memory optimizations like mixed precision and gradient accumulation don't sacrifice accuracy. Now let's look into peak memory usage, highlighting the true impact of these techniques. The standard model shows the highest memory usage. Mixed precision alone reduces memory usage by using lower precision tensors through most of the model. Yet the largest gains come from gradient accumulation, lowering the per-step batch size from 256 to 64 and accumulating gradients over several steps drastically reduces memory usage. These configurations facilitate full batch training on memory-constrained devices. So what does this tell us? Well, first, accuracy remains stable despite applying optimization techniques. Second, gradient accumulation primarily reduces memory usage, with mixed precision offering additional savings. This means you can apply these techniques or combinations of these techniques without substantial performance concerns. A final note: when you run these experiments in the lab, if your experimental results differ, that's normal. Lab code runs in a shared cloud infrastructure, which introduces variability in timing and resources. The focus should not be on achieving exact numbers, but interpreting patterns and trade-offs. As always, the optimal setup depends on your constraints and goals. Is minimization for smaller GPU necessary, or is achieving peak accuracy important? One-size-fits-all solutions are rare, so experimentation and profiling are crucial. Now you've learned to diagnose performance bottlenecks and apply optimization strategies for better memory usage. Whether you're using mixed precision for memory savings, gradient accumulation to simulate larger batches, or a combination of these techniques, the right approach will depend on your specific goals and constraints. Now that you've used Lightning to streamline training and run diagnostics with the profiler, it's time to step back and consider everything this framework has to offer. Formerly known as PyTorch Lightning, its mission remains the same: to help you write clean, scalable, and professional-grade deep learning code that's free from engineering overhead. In the last video, you saw how it cleared away boilerplate from training loops, and that's just the start. There are several reasons why Lightning has gained widespread adoption in both research and industry. First, it enforces a clean separation between model logic and training infrastructure. In standard PyTorch, everything tends to get bundled into a single training script. Model definitions, data loading, device management, logging, optimizer setups, and all that. This can work, but maintaining it becomes complex and messy as projects scale. With Lightning, your training and validation logic reside in a Lightning module, and your data is managed in a separate data module. Both are passed to the trainer, which handles everything else: the training loop, evaluation, hardware acceleration, precision settings, and even logging. This structure ensures consistency. When revisiting the code weeks later or attempting to run it on different hardware, it continues to work as you expected. You don't need to worry about remembering to transfer the model to the correct device, or if a training step accidentally omitted a loss value from logging. Lightning is designed for scalability. Whether training on a single GPU laptop or a multi-node cluster with dozens of accelerators, the code remains unchanged. Configuring a few trainer options allows it to handle scaling up, eliminating the need for code-based rewrites. Additionally, there's an extensive ecosystem. Lightning seamlessly integrates with logging tools like TensorBoard, 1DB, or MLflow, and it offers features for automatic checkpointing, early stopping, profiling, and exporting to formats like TorchScript or Onyx, which I'll explore in the next course. This is just the beginning of what Lightning can do. I encourage you to try it out and explore its capabilities, helping you in your new journey as a PyTorch AI developer. That brings us to the end of this video and the conclusion of this course. Let's quickly recap everything that you've learned across the 4 modules. In Module 1, you explored hyperparameter optimization. You learned to use learning rate schedulers, tune hyperparameters both manually and programmatically. You designed flexible architectures, and you applied tools like Optuna to automate the search for optimal model configurations. This helped you understand how to enhance your model's performance through smarter training strategies. Module 2 focused on working with images using Torch Vision. You learned to load built-in datasets, apply data augmentation, leverage pre-trained models, and visualize experiment results. Torch Vision provided tools to streamline the image pipeline, allowing you to use powerful models trained on vast datasets. Module 3 introduced you to the world of natural language processing with PyTorch. You navigated through tokenization, tensorization, and embeddings, and you implemented your own text classifier. You also learned to fine-tune a pre-trained transformer model from Hugging Face, achieving state-of-the-art performance on text tasks with minimal code. Finally, in this module, Module 4, you focused on building efficient training pipelines. You profiled performance using PyTorch and Lightning. You tuned data loader settings like batch size and the number of workers, and you explored optimization strategies like mixed precision and gradient accumulation. You also saw how Lightning simplifies scaling your training pipeline while minimizing engineering effort. Together, these modules have equipped you with a comprehensive foundation in using advanced PyTorch techniques and ecosystem tools for building, training, and optimizing deep learning models. In the next course, you're going to go deeper into topics like custom architectures and specialized techniques for computer vision and NLP models, enhancing your PyTorch skills. Thank you so much for learning with me. I hope you've enjoyed this course, and I hope you feel more confident using PyTorch for real-world projects. And when you're ready, I'll see you in the next course.